source code quality with the ISO-25010 approach. It's intended for software developers and actually anybody else who is interested in code quality and what it means. The agenda is we're going to go through the code quality traits according to the ISO-25010 standard, and going to go through some of the related source code metrics and show you also the quality metrics where the ISO 25010 traits correspond with certain metrics that you can use in measuring the quality of your software. ISO standard actually defines the software product quality guideline, but not everything actually relates to source code. As developers, we are interested in making good source code, and as an organization that employs us, they want a good software product to use. So the source code is what we write, and the configuration maybe even, and sometimes source code could be visual, could result in visual graphics or backend systems that handles data. So we're not talking about software product in total, because that would entail everything working together, but we're talking really about how to get clean software code that is compliant to the software product quality as defined in the ISO 25010 standards. And the most applicable to the source code in that aspect is a subset of traits, desirable code, source code traits defined in the maintain. So let's look at the ISO 25010 standard and what it entails. So it describes all kinds of software product quality traits and subsets of these, ranging from functional stability, performance, efficiency, compatibility, usability, maintainability, reliability, portability, and security. So not all of these will directly be measurable or influenced by the source code, because it describes the whole product. And what we would like to focus on is really the source code part. You can find this the most relation to code quality in that aspect in the maintainability part. So let's take a step back and say, what is code quality really? Code quality is a goal. There's no definition of exact numbers that tells you, okay, this is good quality code, although there has been a lot of research done in that area, and there are good indicators that will be corresponding with some of these traits that are described. But this standard, the software product quality would just tell you, okay, what is good software, and also explain why. So if they say, okay, modularity, then they would tell you, okay, so there are a few metrics not there are a few metrics, but when you have modular code, when you change one module, it shouldn't impact another module. Right, so the risk of introducing bugs to everything is lower when you have created modules that are independent of each other. Reusability is more for like, do not reinvent the wheel 10 times. If you can reuse some code, then the reusability is an aspect of good software. You can even connect some metrics to it, like duplication. Code duplication would be ill-advised when you are, if you want to do reusability, because then you're not reusing rather than inventing the wheel over and over, and so on. Analyzability would talk something about the readability and analyzability of the code, and you would do that all the time, of course, if you are still working on an ongoing project where the specifications sometimes change or bugs emerge or new features are introduced. So that brings us also to the modifiability, and the modifiability is how easy is the code to modify without introducing new bugs or affecting the rest of the system. And then there's testability. If you have created software and you cannot test it, then you cannot guarantee its reliability. So the software that has to react and behave in a certain way has to be able to be tested that it is doing what it should be doing. So these aspects can actually be measured, and the way to measure them, and to the extent, is what we're going to talk about in the relation to the standard. So as I said before, here's what we're going to talk about: the analyzability, modifiability, testability, modularity, and reusability. And they explain that in to a certain degree on the page. If you go and visit it, just Google ISO-25010 and you will find the specs and you can read this. So analyzability is, as I said before, the degree of effectiveness and efficiency in which a product can be analyzed to assess impact of an intended change, diagnose a defect, identify a parts to be modified. Modifiability is the degree of effectivity and efficiency of which a product or system can be modified without introducing defects. Testability, I just said it in many more words than the short and concise way they are saying it here. So the degree of effectiveness and efficiency when establishing test criteria for a system, product, or a component to determine whether those criteria have been met. Modularity, the degree of independence of components that a change to one component has minimal impact on other components. And reusability, degree to which an asset can be used in more than one system or building other assets. So let's go further in about why we are doing this. So when we are talking about quality is something that companies tend to give value to, and that's not a strange thing because it is all about risk. So when you buy something and you know it's going to break tomorrow, then you'd rather pay a little bit more money and have it work for a very long time without any headaches. That goes for a car, that goes for software, that goes for a good knife. It doesn't matter. It has a functionality, and the quality of it has to be determined in one way or another. So these qualities will minimize the risk you're taking when you are using such software or building such software. So as a developer, I would like to give that quality to my employer or a project I'm working on, or to my other colleagues that are going to work with the same software. So when I deliver software, I would like them to have a good quality code. So these are the factors that are mentioned about how to achieve this, described in traits, not so much in specific architecture or specific language or specific method, but these are the desirable traits to minimize the risk having your software bring up problems. So there is this company called Software Improvement Group, and they have created a product basically, which I'm going to take as an example, not as a publicity stunt or anything. So there is this company that created a product that checks software. It doesn't do that completely because some of the work has to be done manually. So we're going to focus on what they did and why and how it relates to the ISO 25010. Because the subject is quite well researched and I really liked it. So, okay, let's take it as an example. So when we're talking about analyzability, what impacts the analyzability of the code? According to multiple research, there are some aspects to software that makes analyzing a software easier or more difficult, such as the volume. It's a no-brainer really. If the volume, the size of your code base is really big, and we'll get back to what that means in a bit later, then it's harder to analyze because bigger probably does more, right? So the volume will impact it. Will impact the analyzer. Duplication of the code will also make it more difficult. So if you have the same code in multiple places in your code, but it's doing same thing, then it's going to impact the analyzability, because it's harder to read which one is doing what and where and when. And if I have to change, do I have to change them all? Or do I have to change just one for this flow? The duplication of the code doesn't make things easier. It makes the analyzability a bit more hard. The unit size is very similar to the volume, but in this case we're talking about a unit. So a block of code, a method, a class with multiple methods, is a unit. Its size will also say something about how much it is doing. So the bigger the unit, the harder the analyzability, of course. And component balance will also make it more difficult. A component balance basically says that the volume of the code in one place, so if all your logic is in one place, then it's harder to analyze. Probably is going to be a bit more complex, very big, and every change impacts always everything. So if you split it down to smaller parts, balanced in size, then your component balance will be better, because and it will help lessen the impact on the other parts that you have broken it down to. So yeah, these things will impact the analyzability of the code. So we're gonna go further to modifiability, and modifiability will be harder if you have duplication in the code, because if you want to modify a duplicate code, then you have to modify it in all the places that you have duplicated it, which makes not more complex, but probably more time consuming and more error prone. Unit complexity makes things also harder, because here's the thing. Unit complexity is measured in cyclomatic complexity by, I believe, cyclomatic complexity and cognitive complexity. Cyclomatic complexity will tell you something. The higher the number, it will tell you something about the number of tests. So the higher the number, the more tests you have to write, probably test your code efficiently and correctly. So cognitive complexity, on the other hand, it's not about the amount of testing that you probably need to do. It's more about the readability of the code. So stands the reason, the less complex unit is, the easier it is to modify. Because if you need to modify it and then you have to rewrite a lot of tests that will test the one place, then it will be harder to modify with more tests. So many more tests will be impacted as well. What the other point is module coupling. So the more coupling you have between your modules, and we need to know something about module coupling. Module coupling says something about the dependency between modules. So if one module is dependent on three, or three are dependent on one, that will impact the dependent modules. So when you are making a change to one module that three other modules are reliant on, then you are impacting three modules. So the module coupling will impact the modifiability of your code. Less coupling, better modifiability. Testability is the next one. Yeah, the more code, so the volume, the more code, harder it is to test. So the impact on the testability will be greater with more code. Unit complexity, same problem. The more complex a unit of code is, the more tests you have to write, so the testability is impacted in a negative way. Component independence is similar as well, because if I'll get to that one. Actually, it's easier to explain with a graph, and I will get to the graphs in a bit. But it does say, so the more components your component is reliant on, the less easy it is to test. So if you need to, if the component is not very independent and use a lot of other components, then your tests will be more hard to create. And probably also an indicator of a component doing too much. So then we go to modularity, and then the impacts about modularity. This one is actually introduced in the ISO-25010 because the previous ISO, the ISO 9126, didn't have these parts actually. Didn't have the modularity as a trait, but it is necessary because it does have a big impact on how much risk you have when you don't have modules and you have everything in one place. So the impact is always great, and this is introduced in the ISO 25010. So again, the module coupling has an impact, of course, on the modularity. The component balance also has impact on the modularity, and the component independence, we have just talked about it as well. But the component entanglement, so component entanglement says something about the interdependency between two or more components that are two-way dependent on each other. So one component, if two components have like one component has dependency on this component and this component has dependency on this component, then they're both dependent on each other. You need to know, okay, why, what kind of responsibilities do they have that makes them these traits and metrics influence the modularity. Then we go to the reusability, and the reusability is impacted by two metrics: the unit size, so how big the unit size is, and the unit interfacing. And the unit interfacing is one that I didn't know before, but I knew that it existed, I just didn't know the name. It's basically the number of arguments that your method or constructor has. So if it has a lot, then it's probably doing a lot. And you might want to think about, for example, wrapping arguments into a wrapper object and giving it to the objects that you are passing through to. So yeah, the relation between the ISO 2500 and the metrics known to us and usable by us is a good basis to go on and examine your own code. Now, yeah. So, what kind of metrics can we use or how are they called? So, for the volumes we have a metric that's LOC, which is lines of code. Duplication can be calculated by percentages. Unit size is with mlog or clog, so method lines of code or class lines of code. Unit complexity can be measured with cyclomatic or cognitive complexity, the degree of complexity measured in cognitives or cyclomatic. There are multiple implementations, but they do not differ from each other that much. So unit interfacing is the number of parameters. Okay, so let's go to module coupling and the component balance and the component independence and the component entanglement. They demand a bit more imagination, so I decided not to go and just give you the text, but explain using graphs. Let's go through the metric. Yeah, we'll get to those after we go through the metrics that are most commonly known. So lines of code, you can achieve this metric and calculation in many ways. One of them is this simple tool, the clog. Calculate lines of code, and it will show you an overview of the lines of code, which is an indication of the volume. So the volume is an indication of the number of man years used in comparison with the Java number of lines of code. So the keylog is the kilo, which is 1,000 lines of code multiplied by 1,000. So the kilolog for a Java code is, for example, 0 to 66,000 is in relation to an approximate work between 0 to 8 years, and 66,000 to 246,000, 8 to 30 years, and so on and so forth. So this is different per language, which the ranking of which is also different for the lines of code. Yeah, per language, because some languages are more verbose, others are just different, which is why you need less or more code, and they also serve different purposes. So Java versus COBOL versus PLS. The number of years corresponding with the number of kilo lines of codes are just different, and you have to know which one is which for your own for the language you are using. So these are explained like this, and the ranking, I'll come to that later. Duplication is calculated in percentages, so how much of your code is duplicate code. And the complexity, McCabe's complexity, in this case the cyclomatic one, I took for reference because the cognitive complexity is a bit harder to calculate, and you can find enough literature on the internet about it, but let's keep it simple for now. It's about complexity, and it is ranked also in this scale. So in volume, when you're talking about Java code, and it is 0 to 66,000 lines of code, then you're basically in the green because the man years are lower. So when you're analyzing code or changing code or working with code, then this is in the green. If you're making 66 to 246 kilo lines of code, then light green, so you're getting a bit more risk. Yellow, 30 to 80 years, 246,000 to 665,000 lines of code, then you're in a more complex moderate risk. When you go above that, then you're in the high risk category, and when you're going above 1.3 million lines of code, then it's basically unstable code, very unstable, very unreliable. Anything could make your life as a developer hard to analyze and to change. So duplication, similarly also ranked, 0 to 3% is green, 3 to 5% light green, a bit more complex, moderate risk, 5 to 10 more complex, and let's see, duplication 10 to 20 is high risk, and above 20% of duplication unstable. Complexity similar, but I have seen different numbers, like 1 to 6 would be simple without risk, and then 6 to 10 more complex moderate risk, and so on and so forth. Suffice it to say, if you are going above 20, then to 50, then it's just complex and high risk, and above 50 is just unstable. So yeah, the unit size, if you use a metric that shows you a diagram like this about how big your classes are, then you'll get an indication of what's good and what's not. So when you're going to a class with 1,004 lines of code, then you really need to ask yourself, am I doing a good job right here? Am I not putting too much logic in one place? Would that make my code harder to maintain? Basically, maintain is in this area like modify or test or analyze. Then we'll go to coupling. So module coupling and classes coupling. Basically, what you see here is the desirable trait is low coupling, high cohesion. So what does that mean? If we look at the colors at that screen here, imagine that every color, for example, here is a module or a class or a unit. Let's keep it a module or a class, for example. Let's say that the yellow color is one class, and red is the other, and green is the third. When you have a situation where one class is dependent on two, and the other two are dependent on that class again, and going back and forth, then you have high coupling. When you have low coupling, then the dependency is not circular, but still it's not advisable. So low coupling is better. High coupling and low coupling, so low coupling and high cohesion is the most desirable situation you want to be in. So if this class is doing things that are interesting to this class only, then then that's a good thing, because that's called high cohesion. So it's basically you are not exposing too much code to other components in your system, and you're doing one responsibility, and in doing that responsibility you're using code for that responsibility in that class. So how much are you exposing here? The less you expose, the better, and the less you're dependent on other classes, the better. So the low cohesion is you're dependent on other components. You're dependent on other components, either it's functionality or as a dependency. You're dependent on them. That's not a very desirable trait, because it makes testability, it makes modifiability a bit more difficult. So yes, like functionalities that are related to each other should be put in one place, and the less code exposed to other classes and to other dependencies, the better. So let's go to the next one, which is also an interesting one. I didn't know this one exists. I mean, in the back of my head I know the benefits, but I've never really looked at it this way. So component balance says something about how much would you need to change and where would you need to change it to affect the change that is desired. So if everything is all in one place, then you always have to change everything. So if everything is here and you need to make a change here, then this is one big block of code or one big class or one big module, and you always have to do it here. So this component has a big risk, because every time you change it, you're changing everything. And that means it's very easy to break something. If you have many changes scattered over many components, then that's a bit of a better situation, but if you have more codes in this component, but then in this component you have a bit more and here much less, then it's not very well evenly distributed. And that means also if you change something here, that you might impact a big impact on whatever is dependent on this component or using this component. This one is similar as well, most changes in a single large component, and this is the desirable situation. So you distribute the responsibilities and the changes to the components to one or two components of limited scope. So when I'm changing this one, then only these two are changed, or just two. I'm saying it wrong. So when you distribute your code evenly, well balanced over multiple smaller components that are not that the changes are isolated to one or two components when you want to affect it, then that's the desirable situation. So not very big components that might break the system if one of the big areas have been touched. I hope this is a better explanation. So then we have the component independence. The component independence says actually that they talk about hidden and exposed code. The more hidden code, the better. The less exposed code, exposed dependency really. So it talks about like how much dependency. So if your class or your component is dependent on 1, 2, 3 or just one, and it's very limited, so the most of the code in this component is used for here, and even other classes can be dependent on it, that's fine. But if your component is dependent on other components and the number of incoming component is high, then that's a less desirable situation, because your dependency on these incoming dependencies is great. So what you're doing is little, other and what's incoming is much more. So your exposed dependencies are higher. That's a less desirable trait. Recommended practices. So then we are going to the component entanglement. And so this is the recommended practice. Like, these are components, and these components depend on this one is depend on this one, fine, this one is depend on this. So every time it's like a one-way dependency towards another one, right? That's fine. Inadvisable practice is the one below, where, for example, these two components are interdependent on each other. So actually anything affecting this one, this component, will affect this one, and vice versa. So this is ill-advised, and then you should actually think of, why am I putting interdependency between them? They have to be separate and independent of each other. So probably they're doing something wrong. It's when you're analyzing your code and you see this, then like a little light bulb should be turning above your head and advising you not to do that. So we've been quite through a lot of the theory behind the ISO 25 desirable traits and the metrics related to them. What is out of the scope of this presentation is the following. So we have all kinds of platforms and plugins that we can use to show you how this is done, but I will go through these more extensively in other upcoming video clips, because it will otherwise be too long, and I have already had the feedback that this is taking too long already. So I hope I have explained these metrics and their impact clearly to you, so I can go next time and show you how you can do that yourself. How can you measure the quality of your code using metrics that are available to you using plugins. So this will be excluded. The SIGGRID, it's just a commercial product that I have to pay a lot of money to show it to you, so I will not do that one. SonarQube is readily available, and I can show you how it works. Most of you already know how it works, so I don't think I'm going to spend too much time on explaining what it is. And so this goes also for all kinds of other plugins and frameworks that you can use to check your code's quality, and we'll get back to that in a later presentation. I hope this was informative and helpful, and I hope to see you next time. So have a great evening, and see you soon.